When you step out of the scorching summer heat and into a cool, air-conditioned room, it feels like a wave of relief washing over you. The sudden drop in temperature is almost shocking, and for a moment, it feels like magic. But air conditioning is not magic, it's science. And here's the part most people don't realize. Air conditioners don't actually create cold. They move heat. The heart of this process is something called the refrigeration cycle, a brilliantly simple, yet highly engineered system that uses physics to control the temperature of the air around you. Inside every AC unit is a closed loop of pipes filled with a special fluid called refrigerant. This refrigerant has one remarkable property. It can easily change from liquid to gas and back again at temperatures and pressures much lower than water. And it's this constant change of state that allows it to absorb heat from one place and release it somewhere else. The cycle begins inside your home in a component called the evaporator coil. This is a network of metal tubes and fins designed to maximize surface area. Inside the coil, the refrigerant is in a low-pressure, cold liquid state. As warm air from your room is blown across the coil by a fan, the refrigerant absorbs heat and begins to evaporate into a gas. This is the same principle that makes your skin feel cool when sweat evaporates. Evaporation requires heat, and that heat is drawn out of the air. Now warmed and in gas form, the refrigerant travels outside to the compressor. The compressor is the heart of the AC system, and it does exactly what the name suggests. It compresses the gas. By squeezing the refrigerant into a smaller volume, the pressure skyrockets, and with it, the temperature. This is why the refrigerant leaving the compressor is a very hot, high-pressure gas. Next stop, the condenser coil, which is also outside your home. Here, a large fan blows air over the hot coil, carrying away the heat into the outdoor air. As the refrigerant loses heat, it condenses back into aliquid, just like steam condenses into water when it cools down. But now, this liquid is still under high pressure. To reset the cycle, the refrigerant must pass through a device called an expansion valve or a capillary tube. This component acts like a traffic bottleneck, suddenly lowering the pressure of the refrigerant. And as the pressure drops, so does the temperature. The refrigerant, now cold and ready to absorb heat again, flows back into the indoor evaporator coil, and the entire process repeats, over and over, sometimes hundreds of times an hour. This clever cycle was first harnessed for practical use in 1902 by an American engineer named Willis Carrier. His invention wasn't originally meant for human comfort. It was designed for a printing plant in Brooklyn to keep humidity under control so the ink would dry consistently. Cooling was simply a side effect. But once people experienced the comfort of artificially cooled air, the demand exploded. By the mid-20th century, air conditioning was transforming American homes, offices, theaters, and eventually cars, becoming a symbol of modern comfort and convenience. Modern AC systems have evolved far beyond those early designs. Today's units can filter the air, remove excess humidity, and when operating in heat pump mode, even provide warmth in winter. Despite the technological upgrades, the basic physics hasn't changed. Air conditioners don't make cold. They move thermal energy from where you don't want it to where it doesn't matter. One often overlooked function is dehumidification. Warm air holds more moisture than cool air. When air passes over the cold evaporator coil, not only does it lose heat, but the moisture in it condenses into water droplets, which drain away. This is why AC units can make the air feel so much more comfortable, even if the actual temperature drop isn't dramatic. From a power standpoint, the electricity your AC uses doesn't directly produce cooling. Instead, it powers the compressor, the fans, and the control electronics. The cooling effect comes from the refrigerant's ability to absorb and release heat during its phase changes. This is why modern air conditioners can have a seasonal energy efficiency ratio, or SEER, so high that they can transfer several units of heat for every unit of electricity consumed. Of course, there are different types of air conditioning systems. The most common in American homes is the split system, one unit inside, one outside, connected by refrigerant lines. But there are also packaged systems, window units, portable ACs, and multi-split setups that can cool multiple rooms from a single outdoor unit. In large commercial buildings, you'll find massive chillers and complex duct networks delivering conditioned air to every floor. Even in vehicles, from cars to airplanes, the same principle applies, only scaled and adapted to fit the space. On an airplane, the AC system is part of a broader environmental control system, managing not only temperature, but also air pressure and humidity to keep passengers comfortable at 35,000 feet. While AC brings comfort, it also comes with challenges. It consumes a significant portion of the world's electricity, especially during summer peaks. And for decades, the refrigerants used, like CFCs, damaged the ozone layer. Thanks to international agreements like the Montreal Protocol, those harmful substances are being phased out in favor of more environmentally friendly alternatives. Still, the global demand for cooling is expected to keep growing, which means efficiency will be more important than ever. So the next time you hear that outdoor unit humming and feel the rush of cool air inside, remember, it's not a box that magically makes cold. It's a precisely engineered machine moving heat from one place to another, using principles discovered more than a century ago and perfected over decades of innovation. A small miracle of everyday engineering that quietly shapes the way we live, work, and even sleep. Subscribe us for more videos.